Hello, and welcome to The Space Above Us. Episode 110, Space Shuttle Flight 39, STS-37. Go for Grow. Last time, we covered the 10th flight of Space Shuttle Columbia, STS-35. After an agonizing series of delays, including an almost comical number of gaseous hydrogen leaks, Columbia spent over a week on orbit with a payload bay bristling with astronomical instruments. The crew and mission controllers had to get creative when the input displays burned out, but in the end, the mission was still a big success, collecting tons of scientific data that can only be gathered in space. The reason that data could only be gathered in space is because while the atmosphere is nice and transparent to some light frequencies, notably visible light, it's opaque to others, especially those with high frequencies. Ultraviolet light is one of those higher energy forms of light that is blocked by the atmosphere, but it's not the only one. If you keep moving up the spectrum from UV light, you find X-rays. And if you keep going, you find gamma rays. And there's actually nothing past that. You just get more and more powerful gamma rays. But I feel like I should remind you that these are just names that scientists have applied to photons with certain amounts of energy. All these are just photons. They just stop making new names after gamma rays. Anyway, much like UV and X-ray light, which we discussed last time, gamma rays are generated by extremely energetic phenomenon in the universe. Sometimes it's just the breakdown of a uranium atom, which is pretty energetic for its scale. Or sometimes it's a supermassive black hole with a mass of 100,000 suns devouring an entire star system. Whatever's generating gamma rays, scientists want to know about it. And since gamma radiation's energy is super high, that means its wavelength is super small, which means it can't get through the atmosphere, which means we gotta go to space. Unlike last time, however, this observation is not going to be a one-off thing. Rather than placing a gamma ray detector in Atlantis' payload bay, OV-104 will be carrying a spacecraft then known simply as the Gamma Ray Observatory, aka GROW. It will later be named the Compton Gamma Ray Observatory, after Dr. Arthur Compton, who won the Nobel Prize in Physics for studying the interaction between high-energy photons and electrons. Compton's work was critical to the emerging field of quantum mechanics, and all the instruments on GROW rely on it. No disrespect to Dr. Compton, but I'm mostly going to call it GROW just since that's easier. GROW is the second in a series of 4 spacecraft in what are known as the Great Observatories. Each observatory was dedicated to a different portion of the electromagnetic spectrum. We already met the first great observatory, the Hubble Space Telescope, which covers visible and ultraviolet light. GROW will obviously cover gamma rays, and 2 more spacecraft we'll meet in a little bit will cover infrared and X-rays. Gamma rays are so energetic that rather than observe them directly, the instruments on board GROW will instead look for effects caused by their presence, for instance knocking around an atom and causing a flash. This means that there needs to be a lot of stuff for the gamma rays to knock around, which means the instruments need to be pretty big, which means GROW is the heaviest of the 4 great observatories. At a whopping 16,329 kilograms, GROW weighed almost exactly as much as the entire Apollo 17 lunar module. We'll learn about the main instruments of the Compton Gamma Ray Observatory once we're on orbit, so first let's meet the crew. Commanding the flight was Steve Nagel. We've known Nagel for a little bit here, first seeing him fly as a mission specialist on STS-51G and then as a pilot on STS-61A. Well, now he's in the big seat commanding his first shuttle mission. This is his third of 4 flights. Joining Nagel up front was our pilot, Ken Cameron. Kenneth Cameron is from Cleveland, Ohio, and started his career with the Marines. With the Marines, he learned to speak Vietnamese and spent 1 year in Vietnam, including a stint as a guard at the U.S. Embassy in Saigon. When he came back home, the Marines taught him how to fly, and he spent the next few years flying A4M Skyhawks. He then went to MIT, where he picked up bachelor's and master's degrees in aeronautics and astronautics before continuing on to test pilot school. He was flying F-18s, A-4s, and OV-10s at the Naval Air Test Center when NASA came calling in 1984. This is his first of 3 flights. Mission Specialist 1 was Linda Godwin. Linda Godwin was born on July 2, 1952 in Cape Girardeau, Missouri. She earned a bachelor's in math and physics from Southeast Missouri State before continuing on to a master's and PhD in physics from the University of Missouri. Soon after that, she joined NASA's Payload Operations Division, helping to integrate payloads with the Shuttle and Space Lab. She also served as a flight controller and payloads officer during this time. She was selected as an astronaut in 1985, and this is her first of 4 flights. Sitting in the center seat was Mission Specialist 2, Jerry Ross. Like Nagel, we've seen Ross a few times already. Unlike Nagel, Ross isn't even halfway through his career in orbit, as this is only his 3rd of 7 flights. We last saw him on STS-37B, assembling the ease and access experiments in the payload bay. And last but not least, Mission Specialist 3, J Apt. J Apt was born on April 28, 1949 in Springfield, Massachusetts, but considers himself to be from Pittsburgh, Pennsylvania. Apt earned a bachelor's in physics from Harvard and a PhD in physics from MIT, so, underachiever here. After that, he stayed at MIT, where he studied laser spectroscopy as a postdoctoral fellow. He then moved to Harvard Center for Earth and Planetary Physics before heading out west to the Jet Propulsion Laboratory. After that, like Godwin, he joined NASA as a flight controller working in payload operations at Johnson. And that's where he was when he was selected as an astronaut in 1985. This is his first of 4 flights. In what unfortunately seems to be a trend these days, STS-37 hit a number of snags, leading to some significant delays. To be fair, a lot of the delays were really just echoes of the delays from NASA's nightmare summer of hydrogen, but Atlantis still had a few other tricks to keep things interesting. One of them was something new: cracks in the hinges of the door covering the external tank umbilical. Atlantis was rolled back to the vehicle assembly building in late February of 1991 in order to repair the cracks. From what I can tell, this is the sort of thing that likely would have been fine to fly with, but was iffy enough that it just wasn't worth the added risk. In any case, Atlantis was soon out of the VAB and back on the launch pad, and launch day was upon us, April 5th, 1991. The countdown proceeded smoothly, with only a small delay of around 5 minutes due to minor weather violations. At 9:22 a.m., the main engine spun up, the stack rocked forward and back, the SRBs ignited, and the crew were pressed back into their seats as Atlantis lifted off for the 8th time. As we discussed recently, new restrictions had been added to EVA planning in the name of safety. Many astronauts need a little time to allow their stomachs to settle once arriving in the microgravity environment. And since the results of an unsettled stomach could be pretty dangerous in the confined space of a pressurized helmet, early spacewalks were to be avoided. No EVAs could be scheduled before Flight Day 4, and no payload-related contingency EVAs could take place before Flight Day 3. With that in mind, the GROW deploy was scheduled for Flight Day 3 so the EVA crew could intervene if something went wrong. Since we have a few days, let's learn about the instruments on the Compton Gamma Ray Observatory. Starting with the lowest energy instrument, which is still pretty high energy, we have the Burst and Transient Source Experiment, or BATS. BATS was focused on the phenomenon of gamma ray bursts. These incredibly energetic events occur with no warning and with no way to predict where in the sky they will take place. To give you an idea of just how energetic they are, in 2016 a gamma ray burst was observed that in 40 seconds produced more energy than the sun will produce in its entire lifetime. It's kinda crazy. Lucky for us, these typically happen billions of light years away. With the unpredictable direction of gamma ray bursts in mind, BATS is actually 8 instruments, with 1 on each corner of the observatory. That way it can keep an eye on as much of the sky as possible. When a burst was discovered, other instruments, both on and off of GROW, could then be focused on the source of the burst. BATS captures lower energy gamma rays, between 20,000 and 2 million electron volts. Electron volts are definitely outside the scope of this podcast, but real quick, they're both a measure of the energy of a particle and the mass of a particle, since once you get down to individual particles, these concepts start to get pretty blurry. Next up, operating in the region of 100,000 to 10 million electron volts, is the Oriented Scintillation Spectrometer Experiment, or OSSE. As the word spectrometer may have cued you in, OSSE looks for distinct types of light, which tells us about specific phenomenon. In this case, OSSE is looking for the types of gamma rays that are emitted when radioactive elements break down. This will allow scientists to see where in space this is happening. Among other things, this data can be used to determine the sources of heavy radioactive elements, such as supernovas. Next up, studying gamma rays with energies between 1 million and 30 million electron volts, is the Imaging Compton Telescope, or COMPTEL. Unlike BATS, which is just sort of generally keeping an eye out for gamma ray bursts, or OSSE, which is studying components of gamma ray light in order to study radioactive elements, COMPTEL will actually be making images. This is sort of similar to the UV telescope that we discussed last time. COMPTEL will be able to peer into highly energetic regions and see the heart of those processes. The COMPTEL instrument has two layers, an upper scattering layer and a lower detection layer. The upper layer actually interacts with the gamma rays, which scatter in a special liquid. The lower layer then measures that scattering, determining the source of the gamma ray. COMPTEL's job will be to make a gamma ray map of the entire sky. And lastly, the Energetic Gamma Ray Experiment Telescope, or EGRET. EGRET is studying the really high energy stuff, operating in the range of 20 million to 30 billion electron volts. EGRET is sort of the same idea as COMPTEL, but with more layers. As these extremely high energy gamma rays enter EGRET, they pass through several layers filled with a special gas. This produces an electron-positron pair, yes, we're making antimatter, which recombine and can be seen as a spark. The sparks allow the instrument to determine where the ray came from, and special crystals under all of those layers record the energy of the ray. Between all four instruments, GROW will be able to study gamma rays between 20,000 and 30 billion electron volts. When Flight Day 3, GROW Deploy Day, rolled around, it was to be the culmination of years of effort. Scientists and engineers had spent huge amounts of time building the instrument, and the crew had trained for years to deploy it and handle any contingencies. One contingency that was definitely on their mind was related to the solar array. Solar arrays tend to be pretty lightweight, spindly things with complex mechanisms to carefully unfold the large panels. And we've already seen how they can not work as expected back with Hubble. The EVA crew paid special attention to the solar arrays during their underwater training, learning how to manually crank out the all-important electricity-generating panels. Like Hubble, there was a limited time window between disconnecting GROW's umbilical to the orbiter and getting the solar arrays out. With that in mind, Jerry Ross and J Apt had already partially suited up in anticipation of a potential contingency EVA, putting on stuff like their biomedical sensors. Mission specialist Linda Godwin expertly positioned the shuttle's remote manipulator system, grappled the $600 million telescope, and lifted it out of the payload bay. In space and on the ground, people held their breath and watched the solar panels slowly extend, soon coming close to the wingspan of the orbiter itself. But turns out all the drama was for nothing. The solar array locked into place with no problem. Relieved, Mission Commander Steve Nagel made the critical mistake of saying out loud, "Well, everything's downhill from here." The horrified crew turned and looked at him, well aware that there were plenty of things that could still go wrong. It seems that the crew, like a certain middle manager from Scranton, Pennsylvania, weren't superstitious, but they were a little stitious. Sure enough, soon after that, the command to extend the high-gain antenna was given, and nothing happened. Sigh. Nagel. The ground checked that the command had actually gone through, and that it had been properly formatted and all that stuff, while the crew tried blipping the RCS thrusters or wiggling GROW around on the robot arm. But with so much mass, the wiggling wasn't very effective, and the RCS blip was mostly damped out by the arm. Jerry Ross and Steve Nagel came to the conclusion that it was probably time for Ross and Apt to fully suit up for a contingency EVA. Less than a minute later, the ground independently radioed up to suggest the same. Not long after that, with GROW still on the arm, Jerry Ross and J Apt entered the payload bay on the shuttle program's second contingency EVA. Just as a fun coincidence, when Ross opened the airlock hatch, it was the first time it was opened in space since he himself closed it, also on Atlantis, back on STS-31B in December of 1985, nearly 2,000 days earlier. Ross had a long career as an astronaut with a special focus on extravehicular activity, but in an oral history interview, he said that this was the only time he was nervous when exiting the airlock. In 2020 dollars, $1 billion satellite was broken. Ross wasn't sure what was wrong, and it was his job to fix it. No pressure. Godwin brought GROW down a bit so Ross could more easily reach it, and he clambered aboard. The spacecraft was actually made with EVA in mind, so it was covered in handholds. Using those handholds, Ross got to the high-gain antenna and basically just started yanking on it. He estimated he applied around 50 pounds of force, requiring several good pulls. On the third pull, the antenna came free and began to move into place. Only 15 minutes into the EVA, the crisis had been averted. Mission rules dictated that if manual intervention was required, they would stick with doing it manually and not try to return to the automated sequence. So Ross and Apt next retrieved the tools necessary to bolt the antenna into the correct position. Strictly speaking, the high gain wasn't necessary to complete Grove's mission. Just look at poor Galileo. But it would have been a big hassle for the ground to deal with and would have severely limited the amount of data that it was possible to downlink. So this was a big win for human presence in space. The EVA crew stayed outside during Grove's final checkout, getting ahead on some tasks we'll discuss in a minute. But soon, everything was ready. 3 orbits later than planned, around 54 hours into the mission, Grove was released from the shuttle's robotic arm, and Commander Nagel blipped Atlantis' thrusters to back away. The EVA crew was supposed to be back in the airlock for this, but as Ross later tells it, they essentially just hooked their feet inside the airlock and were mostly hanging outside of it, enjoying the show. I guess they technically were inside the airlock, they were just also outside it. After several months of successful on-orbit commissioning, the Gamma Ray Observatory began its science mission and was redubbed the Compton Gamma Ray Observatory. We'll have a little epilogue on Grove later on. You might think that with the primary payload gone, it's about time to wrap things up and maybe make fun of tags again, but we've actually got quite a bit of mission left. After the Challenger accident, EVA expertise began to depart NASA. Some astronauts moved on, along with EVA-oriented engineers, trainers, and so on. This sort of makes sense. They would have known that they were in for some pretty extended downtime before shuttles were even flying at all, and then how much priority was EVA going to get? This brain drain was concerning to the always EVA-minded Jerry Ross, so he started making a push to get EVA back on the schedule. There was valuable work to be done, but it would also be helpful on a meta level to give the EVA people stuff to work on, bring in new people, and get more astronauts outside the spacecraft. Ross and Apt worked together on a series of EVA tasks that would be helpful for future spacewalk planning in general, but would especially be helpful when constructing the still-on-the-docket Space Station Freedom. Both men benefited from an unusual occurrence. They proposed this EVA, helped to develop it, and then were chosen to fly on the mission to execute it, and then chosen to actually perform it. That's typically not how it works. The mission commander actually chooses who goes outside, and in his oral history interview, Ross said he figured Nagel would pick mission specialist Linda Godwin to join Apt outside, in order to help expand the experience base. Nagel said he strongly considered that, and it sounds like if the EVA was the primary focus of the mission, he probably would have gone that way. But with the flagship observatory Grow on board, he wanted someone with EVA experience in case of a contingency. Don't feel too bad though, Godwin will be making her own way outside soon enough. As I mentioned earlier, the EVA crew actually got started a little early thanks to the contingency EVA on Flight Day 3. While Grow was prepared for its release, Ross and Apt operated the Crew Loads Instrumented Palette, or CLIP. This is one of these experiments dedicated to collecting basic data that sort of makes you wonder how they were able to get this far without it. The task here was to just do basic EVA things, while the instruments measured what sorts of forces were required and what sorts of forces the crew could impart. Turn this bolt, now turn it without foot restraints. Pull this lever, that sort of thing. This data would become a baseline for future EVA planning. How do you know if the crew can turn that bolt or grab onto that antenna without breaking something? CLIP. I find stuff like this fascinating. The space program is full of these little imprints from individuals. The Gemini switches were positioned where Gus Grissom could comfortably reach them. The guard around the translational hand controller on the shuttle was sized to Don Lynn's hand. And now the EVAs that built the International Space Station were calibrated to the strength of Jerry Ross and J Apt. The crew made their way back inside after 3.5 hours on their contingency EVA. I haven't run down when this tradition started, if it's still going, or how it started in the first place, but Ross mentions that for some reason, EVA crews make everyone dinner after they come back inside. That's especially interesting this time since they had their non-contingency EVA the very next day to prepare for. This is the only time in the entire shuttle program that the same crew went out on 2 consecutive days. Actually, I didn't run that little factoid down either, but since it came from Jerry Ross, Mr. EVA, I'm inclined to believe it. The EVA on Flight Day 4 was also focused on techniques required for building a space station at some point in the future. As we know from the ISS, a space station can get pretty big, so the goal of this spacewalk was to examine some methods for getting around such a big structure. The method for accomplishing this was the Crew and Equipment Translational Aid, or CETA. CETA consisted of a 46.8-foot-long track and several carts that could be mounted to it. Just on a side note, 46.8 seemed like a weirdly specific number, so I tried converting it to meters and also inches, looking for a round number, and couldn't find one. It seems that it's just a weirdly specific number for no apparent reason. The task today was to use 3 different carts to move along the track, with each one employing a different mechanism to move the crew along. The first one is simple enough. Attached to the cart was a foot restraint mechanism that the EVA crew member would stick their feet into. Once securely locked into place, they would simply grab the track and pull themselves along, hand over hand. The benefit here is they can move the entire length of the track without having to continuously readjust tethers. And this is just me guessing, but it seems like you could also do this with one hand and carry something along with you. The second cart resembles those funny little train carts that I've only seen on, Looney Tunes, though I'm sure they must have had a real use in the past. The crew member would push a large T-bar back and forth to ratchet the entire mechanism forward or backward along the track. But actually, that train car comparison isn't quite enough. The astronaut also had to lock their legs in by placing their thigh between 2 pegs and hooking their feet under another peg. So it actually sort of resembles a piece of exercise equipment. And lastly, my favorite was sort of like the second one, but instead of a big T-bar that you rock back and forth, there's 2 handles that an astronaut would pedal like a bicycle, but with their arms. This generated electricity, which was used to power a motor that moved along the rail. I don't have insight into the design and development process for these tools, but this electric cart thing seems so weird and overly complicated that I really have to wonder what I'm missing. Why convert it to electricity and then run a motor? Why not just use a gear or something? It's also my favorite because when the EVA crew practiced in the pool, there was no motor. A diver would just push them along and they would pretend. This is pretty funny on its own, but it also means that Ross forgot that there was a parking brake that had to be released first. So he's out there spinning these handles around faster and faster, harder and harder to no avail. Linda Godwin reported that he was working so hard the entire orbiter was shaking. Eventually, he realized what he had done, released the brake, and the cart worked as expected. Also as expected, at least to me, the crew reported that the first device was the best. Just pulling yourself along hand over hand was easy and natural. Of course, I can't help but notice that nothing like this track and cart system exists on the ISS today, at least for people. Oh well. When Ross and Apt came back inside after an EVA lasting nearly 6 hours, Apt made a surprising discovery. On top of one of his fingers, near the knuckle, was a small cut with a decent amount of blood around it. He hadn't noticed in all the adrenaline-soaked excitement of the spacewalk. Upon closer inspection, it turned out that what happened was a metallic piece of Apt's glove had broken off, cut his finger, and actually punctured the pressure bladder of his glove, leading to a small leak. The leak was so small that even if it were unobstructed, it would not have been big enough to even trip the backup oxygen system, though the EVA ground controllers would likely have noticed the slightly increased rate of oxygen consumption. However, it was obstructed by Apt's blood plugging the hole. As far as I know, this makes J Apt the only person to ever be directly exposed to space. And with his frozen blood plugging the hole, this minor incident sounds like something right out of science fiction. This flight had its usual share of mid-deck experiments, but we're just going to do a quick check-in. There was another experiment dedicated to growing crystals, which I'm starting to think is just NASA's weird hobby. There was also a much smaller version of the SHARE experiment we saw back on STS-39. SHARE, the Space Station Heat Pipe Advanced Radiator Element, was a test of a passive thermal control system for potential use on a space station. It consisted of a 43-foot-long pipe in the payload bay filled with ammonia and carefully shaped tubes. The ammonia would vaporize, make its way down the pipe, condense, and then make its way back down towards the heat source. On STS-29, it didn't really work so great, and no one was sure why. It turns out some of the angles were just a little too sharp, preventing vapor from moving freely and disrupting the cooling cycle. On this flight, we have SHARE 2, which consisted of 2 miniature versions of the big SHARE, each one about a foot long. The crew could inject bubbles and watch how the process worked through the transparent walls. Neat. We'll be back to payload-based sized pipes with a third share experiment a little bit down the road on STS-43. Flying on the shuttle for the second mission in a row was the Shuttle Amateur Radio Experiment, or SAREX. Pilot Ken Cameron was especially excited about this opportunity to use his ham radio skills to reach out to students and amateur radio enthusiasts across the world. He even convinced some of his fellow crew members to get their radio licenses so they could participate, even if some weren't wild about the idea. Ross wasn't especially interested in the time and effort to get certified, but when the mission was delayed again, he could no longer dodge Cameron's pleading. Once on orbit, he briefly participated in the experiment. After a few perfunctory conversations with the ground, he had fulfilled his obligation to his pilot and returned to whatever other activities he was doing. Ross figures he is the only person in the world to have only made contact going space to ground and never ground to ground or ground to space. Atlantis was scheduled to land on flight day 5, but due to some windy conditions on the ground, STS-37 was extended another day. Free day in space. A day later, the wind was still looking a little iffy, but was within limits, and the decision was made to go for the landing. During the final approach, Atlantis encountered some unusually strong wind shear, pushing the vehicle off of the nominal path. Commander Nagel ultimately ended up landing the spacecraft over 500 feet short of the runway threshold, while flying significantly slower than usual. While this certainly isn't great, it's not quite as big of a deal as it might sound. First, Nagel had in fact noticed the issue and understood the potential impact, but he also knew that he was landing at Edwards Air Force Base. The whole benefit of Edwards is that it's a dry lake bed. You can basically land anywhere. So even if he was way off course, he would still be able to complete a safe landing. So rather than get aggressive with his approach, he figured it would be best to keep things nice and smooth and use the advantages available to him. Why do something drastic to get on the runway if it's not really that important? It turns out that even at the Kennedy Space Center, this would not have been a disaster. Before the shuttle landing facility runway technically starts, there's still 1,000 feet of concrete. So in the end, there was just a minor bruise to Nagel's ego, but considering that he went on to command another flight, it doesn't seem to have impacted his career at all. In any case, after 5 days, 23 hours, 32 minutes, and 44 seconds, Atlantis was home. And with the heavyset GROW on its way, the spacecraft was considerably lighter than when it left Florida. And speaking of GROW, let's find out what happened to it. As I mentioned earlier, GROW was designed with shuttle servicing in mind. It had convenient handholds for EVA crew members, and a propulsion system that was capable of being refueled. Unfortunately, a GROW refueling mission never came to pass. Instead, as it drifted lower and lower in its orbit, and its attitude control system started to have some issues, the difficult decision was made to intentionally deorbit the functioning spacecraft in a controlled splashdown. Typically, at least back then, spacecraft were just left to drift, eventually re-entering in an uncontrolled manner decades later. Since most spacecraft aren't really all that big, and they tend to be pretty light, they would break up in the upper atmosphere, and the pieces would mostly just burn up before getting to the ground. The chances of the debris hitting a person, or a building, or even land is relatively low. But GROW is a powerful beast, with large instruments and heavy metal structural beams. NASA expected around 5,600 kilograms of material to survive the re-entry process and make it to the surface, some of it in chunks weighing several hundred pounds. With the odds of it hitting someone as high as 1 in 1,000, GROW had to be dealt with. Planning a controlled entry when you don't have something like the shuttle's OMS engines to help out is trickier than you might think. This is a whole topic on its own, but here are a few things to consider. How low can you go into the atmosphere before the torque imparted by the tenuous air is too much for your attitude control system to deal with? What happens if there's a solar flare partway through the process, fluffing up the Earth's atmosphere and significantly increasing drag? What if the final burn has to abort partway through? Will you be landing somewhere more problematic? And once the spacecraft breaks up, how far will the debris go? You have to estimate the ballistic coefficient of the resulting chunks and come up with a footprint for what splashes down earlier and what splashes down a few thousand miles down the path. The necessary analysis was done, the burns were planned, and in the spring of 2000, GROW performed 4 large maneuvers. The last maneuver brought its perigee down to 148 kilometers, low enough that atmospheric forces mounted, and GROW began its fiery demise. On June 4th, 2000, at 2:10 a.m. Eastern Time, the Compton Gamma Ray Observatory tore through the upper atmosphere, its debris splashing down harmlessly in the Pacific Ocean. After 9 years of groundbreaking science, its mission was complete. Just one last little epilogue to this flight. Sometime after the mission, Commander Steve Nagel and Mission Specialist Linda Godwin got married, with fellow Mission Specialist Jerry Ross serving as best man. The happy couple were forever doomed to jokes speculating on their status when they flew together, but the crew insists there was no, as one crew member put it, hanky-panky. Though, in his oral history, Ross could not resist joking that he'd tell the real story when the microphones were off. I guess love can bloom anywhere, even at 17,500 miles per hour. Next time, we're back with another Department of Defense mission, and you know what that means. But actually no, this is an unclassified flight. Well, there's a little bit that'll be classified, but not the whole thing. Hooray! Get your sextants and laser rangefinders ready, because Discovery's flight on STS-39 is considered by those in the know to be the single most complex shuttle deploy and retrieve rendezvous mission of the entire program. Ad Astra. Catch you on the next pass.